Live from Earth, it's Space Radio. This is Paul Sutter, astrophysicist at Stony Brook University and the Flatiron Institute, coming to you live here at Spaceman Studios in New York City. We have an amazing show for you today. We are going to talk all about how the Nobel Prize has fallen into a black hole and may not recover. And of course, taking listener questions from around the globe. And in today's Blue Shift, I will talk about the lure of the Nobel Prize. Listen, you want to ask me questions. That is the whole point of this show. And the whole point is for me to pretend to know what I'm talking about and possibly answer them. You can get me questions in many ways. The best way is to go to the website, spaceradioshow.com, and you can leave a voicemail where you will get your question on the air, assuming it's like not full of profanities. And also, you can join the Space Cadets tuning in live from around the world on YouTube and Twitch every Thursday at 8 p.m. Eastern. I have tuning in live from Northern Illinois, Rutherford, New Jersey, Howell, New Jersey, Idaho, Washington, D.C., Canada, London, UK, Australia, Pell City, Alabama, and Cornwall, UK. Thank you so much, all of you wonderful space cadets. Now, this is it. Last week was supposed to be the first show in this new format, this more relaxed format. Auburn University, Alabama, Brasilia, Brazil, coming in at the last second. How you doing tonight? And Veritasium did a video saying gravity isn't a force. Happy to talk about that. I'll get to that. Good question. So yeah, as you can tell, it's a lot more informal. This broadcast is no longer going out as a radio show. I made that decision a couple weeks ago. And so we don't have to stick to times. It's not going to be strict like I need 6 minutes and then the commercial break and then 4 minutes, etc., etc., etc. So we get to have more of a conversation, mostly a one-way conversation because I'm going to do 99.8% of the talking. I will play some voicemails in today's show. But listen, I got some news I want to share with you. And look, I can do a new trick. I can do a new space radio trick. Check this out. I can share my screen. This is amazing. So we're going to go on a journey through the internet together, especially as I share today's news. Okay, this news is 2 weeks old. The Nobel Prize in Physics. I was going to talk about it last week, but ran into massive, random, never unexplained and unexplainable internet connection issues. So I couldn't run the stream, but here we are. And so I still wanted to talk about this because actually there was some astronomy news this week, but it was kind of lame. Unless you guys want to talk about it. But the Nobel Prize in Physics this year went to 3 people. Half the prize went to Roger Penrose, a quarter of it went to Reinhard Genzel, and a quarter of it went to Andrea Ghez. Now, this is a very, very interesting prize. I dug through the history of the Nobel Prizes, and first off, the past 10 years or so, astrophysics the Nobel Prize goes to all fields of physics, so astrophysics, high energy, nuclear, condensed matter, every kind of physics. If you go in a physics building at a university or a lab, there are all sorts of physicists doing all sorts of things. Of course, astrophysics is the best. I'm not going to lie. But it's been like a really, really good 10 years for astrophysics, man. We have claimed a lot of prizes in the past 10 years. We've got like CMB, cosmic microwave background work. We got the LIGO results. We're just, and then now we have black holes. Now, there have been a lot of Nobel Prizes awarded for black hole adjacent topics like the discovery of gravitational waves from colliding black holes. This is the Nobel Prize that really cements in, yes, black holes are real. Now, we've been noodling around with the concept of black holes for decades, like ever since like the 1920s. And of course, there have been hundreds of people working on the topic of black holes on the theory side, on the observation side, but the Nobel Prize is limited to 3 people. And so they made a very, very interesting choice here. They split it between the theorist, like a representative theorist on the black hole front, Roger Penrose, and then 2 observationalists. Now, Roger Penrose was really good best buds with Stephen Hawking, who also worked a lot on black holes, and they did a lot of their best work together about black holes. And it's wondered if Stephen Hawking were still alive, if this would have been his year. Who knows? But what Roger Penrose did, I want to talk about Penrose first. What Roger Penrose did was take black holes from a like very theoretical, hypothetical concept, from a concept that was like, oh, look, in the equations of general relativity, isn't this cute? To all the way like, hey, guys, sit down. I think black holes might actually exist in nature, and I think I know how to make them. He was the guy who led that transition from interesting mathematical curiosity to living nightmare in our universe. He showed how stars, if they collapse under their own weight, if they're above a certain threshold, they will collapse down to form a singularity with an event horizon. They will create a black hole. He figured out that this is a real thing, and then he continued to work on it. He did that work way back in the 60s and 70s. The past 30 years or so, Roger Penrose has been more focused on what he calls this model of cosmology called conformal cyclic cosmology, which largely no one really buys into. Happy to talk about it later in the show if you're curious about it. Also, he's been going on these tangents a lot about using quantum mechanics to explain consciousness. He's not really talking to like neurologists, or biologists or geneticists, or, it's been an odd path for the past 30 years of Roger Penrose, but the award goes to his work in the past of really cementing like black holes as a concept. Yes, Michael, isn't Roger Penrose the guy that believes the universe goes through eons and then starts a new Big Bang? Yes, exactly. Roger Penrose believes that the universe like continually cycles in new rounds of Big Bangs. I'm just going to put my hands up here. Now, the other half of the award, like when you have to pick, like who are we going to pick to represent the observational side of black holes? It could be the Event Horizon Telescope team. It could be LIGO folks, for a round 2. But they went to Genzel and Gez. And these 2 folks, one is based in UCLA, one is based in Hamburg, Germany, if I remember right. And they worked with independent teams, independent telescopes, independent strategies. What they were doing were mapping the very center of the Milky Way galaxy. They were studying a apparent massive object called Sagittarius A star, and they were watching stars orbit this massive unseen thing, and then based on the orbit of the stars, you can calculate the mass of the thing that you can't see. That thing is like 4 million times the mass of the sun. It's huge. It's a black hole. I want to show you a movie actually over here. These are actual observations of stars, or just look at this. Look at this. These are actual observations of stars orbiting something in the center of the Milky Way galaxy. And you can't see the thing, but you can see the stars. Now, this requires massive networks of telescopes and tons of dedicated observing time. This is such a difficult observation. But you can make it. And Genzel and Gez, leading separate teams over the course of decades, were able to map out these star motions, these star orbits, and demonstrate that there's something like right there. There's something right there in the middle that we can't see. And so now we have all these cool movies and simulations like I'm showing here that show us navigating to the center of the Milky Way galaxy, watching the orbits of these stars. Massive observational effort that really cemented, okay, stars, when they collapse, they can turn into black holes, whatever. By the way, there are also giant black holes in the centers of galaxies. Like, that was big. That's huge. That like there's this whole class of black holes. And Genzel and Gez were the two leaders of these massive teams going. I mean, they're still doing it. They're still working on this stuff. So it's an interesting Nobel Prize to me because of all the things that all the people have done when it comes to black holes. They had to pick, ultimately, they wanted to award, like, okay, now that we have Event Horizon Telescope, now that we have LIGO, now that we have these observations, now that we have all these theoretical insights, like, okay, black holes are real. People worked really hard and deserve a Nobel Prize to acknowledge the reality of black holes. So we got to give it to the theory person. We got to give it to some observational person. And they picked these three people. They're all deserving. I'm not saying that, but there are also other people, other groups, other thinkers that would be solid contenders within the black hole category. I'm not going to pick a fight with the Nobel Prize Committee. I mean, I didn't win it again. And I'm not necessarily bitter about that because there's always next year. I'm still young. That maybe they're just waiting. Whoops, that's the show opener. Maybe they're just waiting to give me my big shot. So I'm not going to complain too much because you never know. I need to answer some questions. Get those questions into the chat. I'm going to listen to a voicemail, see what someone has to say. Ooh, Nancy, any guess what the next Nobel Prize in Physics will be for? I'm betting that it's going to be non-astrophysics related. I bet it's going to be in something like superconductor work or solid state physics. They've got to throw a bone to some other field of physics, even though they're not as cool. Okay, we just... those other physicists, they run around, they start complaining that astrophysicists are hogging all the news, which we are because we're awesome. So we just toss them a little bone to keep them happy. They go back to their labs for another decade and they do like interesting, useful things that make the world a better place. But you gotta stroke those egos. Let's get a question in here. I would tell Greg to play the tip. Yeah, we can still say it. Greg's not the producer anymore. Actually, Nancy Graziano is now elevated to the job of producer and chief cheese suggester. I'm not going to let anyone choose cheese for me. Sorry, Nancy, but you can suggest cheese. You'll be the top cheese selector. Let's play the tape.
Hello, this is Steve from Connecticut. In so many science shows, when they're depicting the birth of a new star, you see the protoplanetary disk, I guess, and all the debris and everything, and the star presumably is at the center accumulating matter, and then suddenly it's depicted as just explosively fusing, and boom, there it is, and there's a shock wave that goes rippling out through the dust. I'm curious to know, how does this really look when it happens, and have scientists ever seen it? Thanks.
Oh, I really, really like this question. In fact, I wanna show some because I can screen share now, and like I am not gonna give this toy of like the pillars of creation. These infrared views of star forming regions. I don't know why it's like. There we go. That's a cool picture. This is a young star forming region. You can see a protoplanetary. This is a real picture. This is a real picture from ALMA, the Atacama Large Millimeter Submillimeter Array. You're looking at a protoplanetary disk. You're looking at a baby solar system where the disk has cleared a little bit with some gaps opening up as planets begin to form. This is just a little baby. It's just a little baby. Now, what you had this question of Steve from Connecticut. You had this question of like there looks like, and now the star is born, and it goes and like it clears away all this debris, all this is gunk up there. Yes, that happens. No, that is not the formation of the star. So the gas condenses down and makes a ball. It's not burning nuclear fusion yet, so it's called a protostar. It's called a protostar. Once nuclear fusion happens, it's technically a star. And in some astronomers still call it a protostar because reasons. But even though nuclear fusion has happened and the star is actually born, it's actually ignited nuclear fusion, it's entered the main sequence, it's a thing now, it's a real star, it's still surrounded by material like this. It's still surrounded by this thick envelope. It's still surrounded by a halo. Eventually, that star will get bright enough and hot enough, and it will flare, it will flash. It will have multiple episodes where its radiation will clear away that disk. It's not an immediate process. There is a point at which the light we see, like this light in the center of the image, that's not coming from the star itself. That's coming from the gas surrounding the star. It's hot enough to glow on its own. Is this image infrared or visual fill? This is in the millimeter, sub-millimeter band. So deep, deeper than the infrared, like way down there. Closer to the radio, actually. This light, this radiation is not coming from the star itself. Eventually, the light we see from the system will be coming from the star itself and not the hot gas surrounding it. And it's that kind of breakout phase that those science shows are trying to depict. It doesn't happen in like nuclear fusion and a star is born. It's not like that. It's a much more gradual, much more messy process, but then there is a tipping point where the star emerges and we see its light. Fantastic question, Steve from Connecticut. I like your questions. Let's see what the Space Cadets have to say today. Thank you, Nancy, for curating all these wonderful questions. Zach Perry is asking about this supermassive black hole in the center of the Milky Way galaxy. I said, aren't there supposed to be thousands of smaller black holes in close orbit to Sagittarius A star? Yes and no. In the past few years, we've realized that there isn't just the supermassive black hole, Sagittarius A star, this thing that has 4 million times the mass of the sun, sitting in the center of the Milky Way galaxy, that there are thousands, potentially thousands, tens of thousands of medium-sized black holes in the core of the Milky Way. They're not in close orbit around Sagittarius A star. It looks like those are all stars happening all the time. But in the core region, like say the central 100 light years or 1,000 light years, just the central core, there are a lot of black holes running around. Not surprising because there are a lot of stars running around. There's a lot of star formation. There's going to be a lot of dead stars. And so you're going to lead to a lot of black holes. But they're not right up orbiting like those stars are. We got another question. Tom Bach, how do we know which are neutron stars versus black holes since we can't see either? Is there a very hard line in the mass of the object? Yes, you're absolutely right. When we're looking at, let me pull up, I love this trick. Let me pull up, say, X-ray binary. This will be a good search term for us to show us a very, very cool picture. Yes, I like this picture. Oh, is it big enough resolution? Yes. Here we go. I'm going to share my screen. That thing's loading. Let's look at this picture. Oh, there you are. Check that out. So this is how we detect a lot of the smaller black holes in our galaxy, which isn't, we see the black hole itself because it's black. We don't see the neutron. I mean, sometimes we see neutron stars by themselves. But what we see often, in this case, what these are called X-ray binaries, where matter falls from a companion star onto a compact object, forms an accretion disk, lights up like crazy with tons of energy, enough energy to make X-ray radiation. And so we see this like bright X-ray source in the sky. Now, what can cause that? It could be a neutron star, and it could also be a black hole. We can tell the difference in two ways. One, we can look at the profile of X-ray energies. The profile of X-ray energies, like at the edge of the disk, the middle of the disk, and the center of the disk. If the X-ray energies keep going up and up and up, even at the center, then we know we're dealing with a neutron star, because neutron stars like emit a lot of X-rays. If it goes up, 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 and then at the very center, the X-ray emission goes away, then we know that there's a black hole in the center, because black holes have a very hard time emitting in the X-ray. And another way we're able to tell is by looking at the speed of the accretion disk. We can tell how big of a mass is in the middle of it. And if the mass is like, say, 5 times the mass of the sun, there's no way that's a neutron star. Neutron stars can't hold themselves up with that much mass. And so it has to be a black hole. So we have multiple techniques to determine if it's a neutron star or it's a black hole. The very first X-ray source spotted in this way is in the constellation Cygnus. It's called Cygnus X1. And for a while, it was up for debate if it was indeed a black hole or a neutron star. Turns out it is a black hole. Awesome question. Let's go back to the phone lines. Let me hear another voicemail. Who do we got? We got Michelle.
Hi, Paul. Michelle here. I need a couple more definitions. You provided a couple for me a few weeks back, and now I need more. Today, I'm curious about a pulsar and a quasar. Are they at all related? Once you help me figure out what exactly they are. And are they ever considered stars or star-like? Your wisdom is always appreciated. Thanks. Looking very much forward to listening to the answer next week. Thank you.
All right, Michelle. Very cool questions. Like, there's so much jargon in astronomy. There's just so much jargon. I can't blame you for getting confused about all this, because it can be overwhelming. It can just go nuts. So let me break it down for you. A pulsar is a kind of star. A pulsar is a dead star. A pulsar is a kind of neutron star. Neutron stars are big lumps made of neutrons. They're a few miles across. They're the leftover bits of giant stars. They are freaky objects. They're dead leftover remnants of giant stars. Sometimes they spin really rapidly and have like beams of radiation that shoot out and blink across the Earth, and they look like they're pulsing or they're blinking, hence the name pulsar. So pulsar is a kind of neutron star. We also have quasars, which are totally and completely 100% unrelated to pulsars. Again, I'm not in charge of jargon. Yeah. No comment. Quasars are what happens when a giant black hole in the center of a galaxy is feeding and it's spewing out tons of radiation. It's so hot and it's so bright. They get the name quasars because when they were first spotted using radio surveys, that they were blobby, they were small, but they were bright. They look kind of like stars, but they were objects. They were quasi-stellar objects or quasars. Now we know that they're giant black holes. But the name stuck. The name was given in the 50s by observational astronomers who didn't know better. And so the name stuck. And that's just what it is. So pulsars are like, these are a certain kind of neutron star, and quasar is a giant black hole that's feeding. Dobby Dazzler is asking, as cosmological data and our use of it advances, which mysteries are we closer to solving, in your opinion? I wish I could say we are close to solving the mystery of dark energy. I feel like we're getting closer and closer every year to figuring out what the heck dark matter is. For a long time, we thought it was going to be a WIMP, a weakly interacting massive particle. That's seeming less and less likely. I see axions becoming more and more favored as the years go by. So we have some candidates. We have some searches. Like we're hopefully going to find figure out what the dark matter particle is. I'm not saying it's going to be easy. But we're going to figure it out eventually. So I feel like we're close. I feel like we're close about dark matter. When it comes to dark energy, we're just so far out there. I don't know. I would honestly be surprised if we figure out dark energy in my lifetime. Yeah, I'm saying decades. I'm saying decades. And you know what? We may never figure out what dark energy is. That's what scares me. Because when it comes to dark energy, like, we have no clue what it is. We have no theoretical insights. Our observations aren't telling us a lot that we didn't already know like 10 or 20 years ago. So it's a sad state. So I'm hoping dark matter gets cracked soon enough. Campbell Duncan is asking, if the moon tastes like the Earth, do other planets taste similar enough to us as well? I remember this news story about like the moon tasting like the Earth because it has a similar chemical composition. Astronauts have reported, the people we sent to the moon and got to like rub moon dust on their fingers and like shove it up their nose, say it tastes faintly like gunpowder. And the vast majority of the Earth does not smell like gunpowder. So I'm not exactly like confident about that news story. Other places certainly have their smells. Venus smells awful, I'm guessing, because of all the sulfur. Titan probably smells awful. I wonder what the oceans of Europa smell like, if there's some interesting chemical cocktail in there. Anyway, like, I'm almost out of time. I'm going to keep chatting. And don't worry, I got my weekly cheese here, and we can keep answering questions during the cheese part. But I did want to talk about my little blue shift topic. Blue shift is my opportunity to get a little bit closer to you. And I wanted to talk about the lure of the Nobel. Like, there is no mistaking that some scientists are gunning for a Nobel Prize. Like, they want to put something out there that wins them the Nobel Prize. Maybe not this year, but maybe in 5 decades if they're still alive. There is no doubt. A lot of scientists know that their work is not going to lead to a Nobel Prize, or if it does, it will only be accidentally. Like the people who found dark energy, they were not working on a Nobel Prize. They were just working on some very, very interesting cosmological question. And then they ended up winning the Nobel Prize because they discovered dark energy. Most scientists are not gunning for a Nobel, but some are. And that's when I see big results like phosphine on Venus. That was a paper angling for a Nobel Prize. Not now, but like years or decades from now, once the result is confirmed. And so I see this like endless cycle of like big flashy result, putting it out there, making a case like going way beyond what the evidence would suggest or what a conservative discussion of the evidence would suggest, just to be the first one out the door. Like they're staking their claim to it. They're sticking their flag on it. They're saying, you know what? Boom, there's life on Venus. All right. I can talk to my assistant to set the travel arrangements. But I find that really destructive because it leads to these giant flashy headlines that then dissolve or disappear in a couple years or a couple months. But people get all excited and then it goes away. And then everyone gets all excited and then it goes away. And then everyone gets it. And so it feels like scientists are just chasing the craziest thing out there, but really that's what grabs the headlines. And the reason these scientists are writing papers and talking to the media like this is because they want it to be true so that they can win a Nobel Prize. If there's a Planet 9 out there, someone's going to win a Nobel Prize. If there is life on Venus, someone's going to win a Nobel Prize. Just et cetera, et cetera. And it I need some cheese to calm down. Oh yeah, Corey, Veritasium did a video saying gravity isn't a force. I'll do that while I'm enjoying this cheese. Today's cheese, I am equal parts intrigued and horrified. This is from Montchèvre. Which means Goat Mountain. if you're curious. This is, although it's not from France, this is from Saputo Cheese USA in Lincolnshire, Illinois. This is a goat cheese, as you might guess. It is, I don't know, can you read that? That is spiced pumpkin flavor goat cheese. Can we just, like, I was surprised. Now, I love fall. I'm all in on fall. I'm not big on the whole pumpkin spice thing because I don't really drink coffee or anything, but like, here we are eating spiced pumpkin goat cheese, talking about if gravity is a force or not. Now, I decided I made a very critical choice because I need a vessel. I need a platform for this cheese. I decided to go with a graham cracker because you know what? If like at best or at worst, the graham cracker is going to mitigate the impending disaster that is this cheese. And at best, it's going to highlight it. It's going to make, if we're going to go sweet and pumpkin spicy in our cheeses, like I'll have like a cinnamon cream cheese, like a cinnamon sugar and cream cheese, like a sweet maple syrupy thing. I wouldn't bat an eye at it. And this package is very hard to open. Now, Corey, is gravity a force? Like, yes, gravity is a force. It's a fundamental force of nature. But it's not a force in the sense that, in the senses that we currently understand forces. We have the three forces of nature: strong nuclear, weak nuclear, and electromagnetic, that we understand through the viewpoint of quantum field theory. And then we have gravity, which we understand as, bending and warping of space-time. So it's tempting to say that gravity, the force, is an illusion because really we're all in free fall, but we're actually following curved trajectories in space-time, but really we're in free fall. And so you don't actually feel gravity the same way you feel forces. But two things. One is we know we do not have a complete description of gravity because we do not have a quantum description of gravity. So it could very well be that we find a description of gravity that sits above this whole space-time bending and warping thing. And it looks exactly like exchanges of particles, exactly how we understand the other forces. And two, yes, we describe it as, oh, you're in free fall, but then you respond to the bending and warping of space-time. Well, you respond to the bending and warping of space-time, that's called a force, right? If I have mass and then something happens to me to give me an acceleration, that is a force. Whether that something is someone shooting a laser at me, or a nuclear bomb going off, or me responding to the bends and warps of space-time, it's a force. So saying gravity is an illusion or gravity is not a force, I think is like just not right. It's not right. So let's try this cheese, which might also be not right. And I don't want that much cheese on my cracker. I gotta start small with this. Here we go. You know what it tastes like? Crazy enough. Because I can't decide if it's good or bad or not. Because, goat cheese is super tangy, right? Which is normally a good thing. And I was scared of it with having a super tangy cheese with this spiced pumpkin note. You know what it tastes like? And you can see the texture here. Oops. I just spilled it over my desk. You can see that standard goat cheesy texture. You know what it tastes like? I'm not joking. The whole combination of spiced pumpkin with the tanginess of goat cheese, it seriously tastes like apple cider. It seriously tastes like apple cider. It tastes like I'm eating apple cider. No, it's not bad. You know what? I'm glad I did that. I'm glad I did this episode. And remember, go to patreon.com/pmsutter to keep this show going. Thank you, Nancy Graziano, for producing this week's episode. Next week, we have a guest. Very, very excited. Tune in next week, 8 p.m. Eastern. and I'm gonna have more of this cheese